This video will demonstrate the grid monitor application developed jointly by OSIsoft and University of California, San Diego. There are 3 steps in our method for detecting and analyzing events on the grid. The first step is event detection. We developed an adaptive autoregressive model of events on the grid. This model is automatically updated when the system is in a quiescent state. It also includes a model of the rate of change of the variables involved, which include frequency, angle, and power. From the autoregressive model, we predict 1 step ahead of the expected value of the output. We calculate the error between the predicted value and the measured value and determine if that prediction error is outside a band of 6 sigma. If it is, we declare this an event. The system marks the beginning of this event using pi event frames. The event is recorded, typically for 30 seconds after the first detection. Events identified in step 1 are then used in step 2, where we identify a low-order dynamic model of the system. Typically, multiple sets of input data and multiple sets of outputs are used. The system is identified in the state space representation in the classical modern control theory approach. We identify the order of the system automatically by the identification algorithm, which is known as realization. Once we have the state space representation of the model, in step 3 we compute the damping coefficients and the modes of oscillation and their participation. These results are then displayed to the operator. Now we'll show you how we visualize these results using PyProcessBook and MATLAB. We've sped up the playback by a factor of 4. We've also included a number of display elements to depict the grid state and provide context for the results of the model. First, note the phasor clocks on each of the buses. These depict the unwrapped phase angle of the bus relative to the reference angle. Now watch as the first ring down event occurs. Note that when the grid is in a faulted state, the buses turn red to indicate the fault. A few seconds after an event starts, our analyses of stability and damping for the event are displayed in the 2 rectangular areas in the lower right. These graphs persist for about 30 seconds after the event to give the operator a chance to review them. Also note the phasor angle difference elements on the lines connecting each bus. Here the second event is underway. Again, note the stability and damping results, in particular that the damping of the mode around 0.4 Hz is less than 10%. This has been indicated with the data point in red. We're now watching the third event. Note the pole locations in the stability plot. The closer these poles are to the vertical axis, the more the system is approaching an unstable state. The closer they are to the horizontal, the more damping the system is exhibiting. Also note the speed of the phasor clocks. The farther away the grid is from a stable state, the faster these clocks will spin. Welcome to PMUCSD, a MATLAB application for the analysis of PMU data written by Professor Raymond DeCalifon at UCSD. Here we're selecting a CSV data file for Case 1. Once the data is loaded, the number of PMUs is indicated, and data for a specific PMU can be plotted from the drop-down menu. This tool can automatically detect events in our data. 7 events have been automatically identified. The user can zoom in to inspect if the automatic event detection has picked up important events and whether the beginning of the event has been marked correctly. If events are not interesting, they can be deleted. Once events are marked, the GUI allows the analysis of events by a simple click on the Run button. Once the event is selected and the Run button is invoked, the user can modify the start sample or number of samples to skip from the event for the analysis. The user can choose different model orders to inspect the fit. Once satisfied, the analysis results can be imported. Analysis can be done quickly for each subsequent event or automated to run automatically as we demonstrated in PyProcessBook. Thanks for watching.